Okay, thank you very much, and I want to thank the organizers. This really has been, one of the best workshops I've been to. Some really exciting experimental data and stuff have come out. So I'm going to talk about some stuff that was done with Bhuvnesh Sundar, which was a student of mine who's now at postdoc at Rice, and then Michael Lawler and Todd Rutkowski, who are at Binghamton University near Cornell. All right, so I always like to tell you the entire story on the first slide so that you can tune out and don't have to listen afterwards, check your email, etc. So the setup is we're going to have atoms with large spins in optical lattices in limit of 1 atom per site. We're all very used to at this time that you get an effective spin model out of these. I'm going to talk about how to introduce an off-resonant photo-association beam, which is going to convert this spin model into a dimer model, and then look at its phases, and we'll get some interesting dimer crystal phases and possibly some spin liquid stuff. So that's what's coming in, and there's lots of details. Okay, so I'm going to begin just talking about dimer models. Why on earth would you care about dimer models? What's interesting here? I'll talk about how to engineer them, and then the details. Okay, so I'm going to go back to 1949, Linus Pauling, I think before he was into vitamin C. You're all very used to this motif from chemistry of you can describe quantum states of certain molecules by talking about where their bonds are. Okay, and you get, in fact, some quantum resonances between different bond patterns. In 1949, Pauling decided to apply this chemistry picture to solid-state physics and tried to come up with a model of metals and some, I think, correlated metals even, by thinking about these sort of resonating bonds. I don't think it was a very good idea, but but it was inspirational. And about 15 years later, P.W. Anderson was trying to understand the Heisenberg model on a triangular lattice, right? And this is, of course, another story you guys know very well. I'll say it anyways because it's nice to just repeat these little tales to ourselves. So if you're looking at spin 1/2 Heisenberg model on a triangular lattice, you throw down one spin up. Look at a neighboring site. Well, probably the best thing there is a spin down, right? Well, now we're frustrated. We don't know what we're going to put here because if we put down, it's happy with this guy but unhappy with that guy. Okay? So what P.W. Anderson said is, well, let's use this idea of Pauling's, and let's just take pairs of sites and we'll just form singlets. All right? And he wrote this down as a variational wave function, took a quantum superposition of all these singlets, and he got actually a really good energy. So this appeared to be a pretty good model for what's happening in the Heisenberg antiferromagnetic magnet on a triangular lattice. Great. 15 years later, high TC is discovered. You have a hammer. Perhaps high TC has something to do with this RVB state, and a lot of people have ran with that idea. A year after Anderson came up with his idea of applying RVB to superconductivity, Roxar and Kivelson sort of did the mathematical formalizing of this sort of model, and thinking about Hilbert spaces where you label the quantum states by a bunch of bonds connecting sites. And they think about if I specify another set of bonds, it's orthogonal to this. And they came up with what is now the canonical dimer model that people play with. And I'll show you what that is in a short bit. And there's really some rich physics they found. There was interesting crystalline symmetry breaking phases as well as some liquid phases. And in the modern parlances, these liquid phases are interesting because they're topologically ordered. And there's some of the nice examples of topologically ordered states that we have. All right. And basically the rule in writing down states is I can write down any pattern I want but I can't have any site involved in more than one bond. Right? This is an analogy to these spin singlets, which you can't make a spin 1/2 in a spin singlet with more than one other spin. Right? Okay. So this seems pretty esoteric. Why is it interesting? And it's actually a good example of a general principle that if you take quantum mechanics and add constraints, interesting things pop out. And it's particularly successful when you think about geometric constraints. So here, by a geometric constraint, I'm meaning that if I put a bond between these two sites, I'm not allowed to put a bond between those two sites. Okay. And I don't know if this is going to resonate with everyone, but one way I like to think about how adding constraints makes rich physics with quantum mechanics is actually thinking about some quantum computing things, about stabilizer codes, error correcting codes, which essentially you take some bunch of spin 1/2 and you add constraints, and lo and behold, you add enough constraints, you get your information delocalized, and it's protected from any local thing you could do to it. Right? More generally, a lot of rich physics has emerged from trying to understand how to implement constraints in quantum problems. So a lot of, whenever people talk about emergent gauge theories, that's typically about trying to implement constraints.
So all these constraints on the dimers, this is just a snapshot, right? So as a function of time, they'll fluctuate and form bonds with another one.
Yeah, if you're thinking about eigenstates, they're going to be quantum superpositions of these different things. Or if you're looking at dynamics, if you did start in one of these, you'd expect it to evolve. Absolutely. Thank you. Okay, so now this is the point in the talk where I should go and enumerate all the wonderful physical examples we have of these dimer models. And unfortunately, there aren't a lot of them. Right? And there's some actually good real physical reason for this. So if we go back to Anderson and think about these bonds as being formed by singlets of spin 1/2 particles, okay, there's a problem is that formally speaking, if I write down a state where I make singlets between these two sets of sites, and I write down another state where I make singlets between these two sets of sites, it turns out these aren't orthogonal. Right? They actually have a very large overlap, and I'll show you that in a second. And so that means that these kind of Roxor-Kivelson dimer models are not really realizable in a nice way by spin 1/2. Well, that's easy, you say. Let's go to a higher spin. All right, so imagine so here's the story. So here's the calculation. When I gave this talk to practice it to my group meeting, I made the students go and do this calculation. I'm not going to make you do it, but you can trust my arithmetic. So what I mean by this state here is that I form a singlet out of these two, and a singlet out of those two. And that's the quantum state I'm writing down. This one is this guy. And if you just multiply this out, you get 1/2. Right? So the overlap is quite large between these. Okay? And as I said, one solution is going to higher spin. So if I do the same thing with higher spin, so by this I'm meaning I'm making a singlet out of these. And if I write down all my Clebsch-Gordon coefficients and multiply it out, I get that this overlap is 1/2f plus 1, where little f is the spin. Right? Or you can recognize 2f plus 1 as the number of magnetic sublattices, sublevels. Okay. And so you go to large enough f, you're going to have these are essentially orthogonal. Okay. The problem with going to large f is that if you look in electronic systems, which have some local spin, which is some moderately large f, the types of interactions you naturally get are not ones that favor singlets, rather than ones that favor a more classical nail order, typically, right? And you can kind of understand this, that one of the major sources of interactions between the spins is really exchanging a fermion, and that changes your local spin by like 1, right? And so you just make small changes to your spin, and that tends to make them look very like classical spins, right? So we're looking for a large spin system which is not just turned into classical guys sitting there. Okay? And so that motivates trying to think about cold atom systems and trying to engineer something there. Okay, so the starting point is something very familiar. I'm going to put one atom per site, and I'm imagining they have some large spin. And we're going to get our standard spin model from some super exchange. That one of these guys hop over there, they interact for a while, then hop back. Okay? And generically, if I'm working in at zero field, so that you have rotation symmetry, we can write this effective spin model completely generically by decomposing the total spin that you get when this one particle hopped over there. So I'm going to let capital F be the total spin of these two little f atoms. So say they were spin 2, capital F could be 0, 1, 2, 3, 4. And we can write the effective Hamiltonian as we sum over all of those values. And we have some coefficient, which is second-order perturbation theory, and a projector into making those pairs into that spin. Okay? And if you look at something like rubidium, these UFs are roughly all the same. If you look at lithium, they have a little more of a spread. And what we're going to want to do is we're going to try and find a situation where the F equals 0 term dominates. Right? So we want a negative term that wants to have nearest neighbors be in singlets. Okay. And as I said, for typical atoms, these UFs are all roughly equal. And so we need to somehow engineer things so that the U0 is much smaller than the other U's. Okay. So here's the crazy idea, and this is the I'll say more about it a bit later, but this is the place where I'll be attacked. Which is, so one way to try and engineer different coupling constants in these different spin states is to use some sort of Stark shift. Right? So imagine we have our two scattering atoms, which are inside one well of this optical lattice, and there's some molecular state. If we shine an off-resonant photo-association level, that's going to shift these things, this level a little bit. And if the quantum numbers of these scattering atoms, if you can make it so that only for certain quantum numbers they're going to have this coupling, you're going to shift the state with those quantum numbers. Right? In particular, if this molecular state has a well-defined electronic spin, that's S equals 0, right, then we're only going to couple to it if these guys are an electronic singlet. Okay. And so if you look at the molecular physics, essentially what we need in order to get a well-defined electronic spin, we need a very weak spin-orbit coupling. Right? So we need a relatively light atom, something like lithium works well, or sodium even is not so bad, that there are some molecular states which have this property in either of those.
Eric,
yeah.
These atoms already close to being formed a bond in the ground electronic potential, because if there are two independent atoms, you'll have a singlet triplet mixtures at large distance.
Yeah, so these guys are in a single well of an optical lattice. As I said, this is the part I'm going to get attacked by, attacked on the. I think I'll talk more to you later. So maybe the short answer.
Eric, let me ask
Yeah.
something else. You said all the U's are equal. If we have fishbowl resonance, we can maybe tune one U, which means spin up and spin down, and we could even use the fishbowl resonance to tune it that maybe the U1, U up down is 0 or close to 0.
Yeah.
But this is not the singlet. It's just.
I know.
It's making hyperfine states in the magnetic field, and you don't want the magnetic field which breaks here.
I know exactly. So here I'm wanting the rotational symmetry.
So it's really the fishbowl resonance where we would have
Exactly.
But this is not
Exactly. But I want this rotational symmetry. Right? And I want to exactly. That's what I said. And in some ways this is one of those silly theory talks where, you know, I'm off in some land of something that's really hard. But it's you know, and I'm fully aware of that. But I think it's useful to interject some thinking about, you know, what is the possibilities and why would this be interesting, and, you know, it's if you don't speculate and try to argue for why something's interesting, then you never bother doing it. So right, yeah. So you know, with the caveat that, you know, there's a lot of stuff going on in the molecular physics. You know, the likelihood of having a single line up here that you're coupled to is pretty low, etc. But if you're really naive and just do second-order perturbation theory, you're going to get a shift of your on-site interaction by some coefficient, which is going to sorry, I misspoke when I said this only couples to the f equals 0. This actually couples to all the f's, but it remains rotationally symmetric, so it doesn't mix the different f's. That's really what I want to say. If this was not an electronic s equals 0, you'd end up mixing the different f's, because there's a directionality of the polarization of the light that comes in. Right, so that's really why I needed the s equals 0. Okay. Right, so you're getting a shift that's been proportional to your intensity of your laser and inversely proportional to your detuning. And you can do a little exercise in Clebsch-Gordon coefficients and calculate how these coefficients should be. And the key point is that they're a monotonic function of this big F. Right? So if initially all of these background U's are the same, you can tune this term in principle so that the U0 becomes very small, but all the others aren't made small. Right? And we just looked at some typical experiments looking at photo-association and the strength of those lines and the lifetimes, and came up with this estimate of a few watts per centimeter squared should be enough to do this, though I fully admit there's lots of little things in there which probably need to be thought about harder. Okay. Anyway, so if you allow me to do this and get to where we only have this attractive interaction in the spin singlet channel, right? This model, this Hamiltonian, the space of singlet bonds, labeled by these singlet dimers, is going to be closed under this Hamiltonian. So I'll show you a little bit how that works. Okay. So I'll just use a set of 6 sites. This is, I think, enough that I can get my head around it. So if I take, so these are summing over all nearest neighbor terms. So if I look at, say, a nearest neighbor term where I look at site 1 and 2. All right, the state I wrote down here, well, site 1 and 2 form a singlet already, so this is an eigenstate. Great. Well, what happens if I instead act on 1, 4? All right. Well, after acting on 1, 4, I have to end up with a singlet on there. It's a projection operator. Okay. This operator is rotationally symmetric. This state is rotationally symmetric. So the thing I get in the end has to end up being a singlet. All right? I can't possibly be messing up anything that's happening on 3 and 6. Right? I'm just acting over here. And so the only thing that can happen is I have to form a singlet out of the other ends of these 2 bonds. Right? So the term in the Hamiltonian that's a projector on these 2 goes and flips this plaquette. Okay? We actually get something a little bit different if I think about, well, what happens if I worked on this bond here at 2, 3? Okay? Well, by the same argument, I'm going to end up with a singlet on 2, 3 And by the same argument, I'm going to act with a singlet between these guys. So even though the Hamiltonian only has nearest neighbor projectors, I end up with longer range singlet bonds, right? But the space of all things, all different patterns I can write down like this, including long range things, that's closed under this Hamiltonian. Okay? Yeah.
So these long range singlets can in fact be arbitrarily long range if I act on the right dimer configuration?
Exactly, exactly, and so but the Hilberts, if I specify, if I write down all possible, including long-range bond configurations, that space is closed under this Hamiltonian. You got a complaint?
There's a little problem.
Yes.
Spin half a little bit is unusual, but if I higher spins, there are 3 particles singlets and 4 particle singlets. So I can actually, there's a because you just add up angular momentum. So there once you
Absolutely. So this does not exhaust the space of all singlets. Okay? But this is a space that's closed under this Hamiltonian. That I cannot, by acting with operators like this, I cannot generate any of those other ones. Because I just demonstrated, right? This is if I act on 2 sites that already form a singlet, I get back what I had before. If I act on 2 sites that don't form a singlet, well, they form a singlet, and then the other ends form a singlet. Right? I mean, it's also, you can just sit down and do the Clebsch-Gordon coefficients as well. I mean, that's how we get the 1 over 2f plus 1.
And do you think the ground state is in this subspace?
Ah, good question. Well, so one thing you notice is that if actually this is a nice slide for this. Okay, so if I look at if I take some configuration here, and I look at all the terms here which act on sites, on bonds that I already have occupied, right? That's a diagonal term, and that makes this, if I have only nearest neighbor singlets, that gives you a large negative number here. Anything else I do is going to give me a less large negative thing, right? And so in particular, in the limit where little f is really, really big, that has to be the best. Right? So I can't guarantee without thinking harder that as f becomes small, you're not going to get some crossover, that something happens. Okay, so if I think about a large f limit, as I said, we're going to have a low energy space defined by making these diagonal terms large, which is just the nearest neighbor singlet space. Okay? Then we're going to have terms which move us out of this low energy space. If f is large enough, we can neglect these or take them into account in second order perturbation theory. And then we have terms which move us around in this low energy space. Okay? And these sort of moves that we get are just flipping plaquettes. And for those who are familiar with Roxar-Kivelson, that's exactly Roxar-Kivelson's model, is that you take plaquettes and your Hamiltonian, you can flip them. And then if you do second order perturbation theory on these guys, you end up getting a term which penalizes having parallel bonds. I'm not going to actually do things in perturbation theory, but it's just nice to know that this model maps onto Roxar-Kivelson. Okay, so what are the states you get from this model? So if I go to the large F limit, what I expect is that I'm going to get a dimer crystal phase, where you're going to get mostly nearest neighbor singlets, and they're going to line up in these sort of ladder type things. And the reason why these are favored is those plaquette flip terms. This is the kind of state that has the most allowed plaquette flips. Right, that all of these are flippable plaquettes. When, for instance, if I had a staggered, if I had a bond here and a bond here, I wouldn't be able to flip this plaquette, and so I'd get less kinetic energy from those terms. Right, and this is known from the Roxar-Kivelson model. The triangular lattice is a little more complicated. It turns out that the ground state, as f goes to infinity, again from studying the Roxar-Kivelson methods, models, this is in the literature, is actually this what they think they call the root 12 by root 12 phase, where there's a unit cell that has 12 sites in it, and it is in a quantum superposition of two different shaped sets of plaquettes, where each of these plaquettes represents the resonating bonds. Yeah, this is far from obvious that this would be true. Right? But it's really exotic. I mean, seeing this would be cool.
So do you have a sense of how big the gap to excitations is for this?
It's pretty darn small.
Something from J over 12 or J over root 12, would that be a decent way to think about it?
Well, there's also this 1 over 2f plus 1 thing floating around. So I think it's even smaller in that. I think you also get that factor. Well, it's not 0. Oh, I guess an f goes to infinity, yeah, but yeah, anyways. All right, so what we did is we're working with our finite f system. You know, we're not going to find an f equals infinity atom around, probably. If someone comes up with one, let me know. So we're gonna do a small system, do some, you know, write down. We have this Hilbert space, write down the Hamiltonian is a big matrix in the Hilbert space and diagonalize it. Right. So we're going to be limited to pretty small systems. And to see what sort of phase we have, we're going to look at this dimer-dimer correlation function, where we look at the projector on two separate sets of bonds. Right. So I look at the projector of these guys to a singlet and the projector of these guys into a singlet. And more or less, you can think about that. What we're calculating is, you know, what is the probability of finding simultaneously a singlet here and a singlet there. Okay. And to visualize it, what we're going to do is we're going to fix one set of bonds and change the others. And so I'm going to draw little pictures where between every pair of sites, I'm going to draw some colored thing, which represents what is the correlator between this pair of sites and that pair of sites. Is that cool? All right, so it'll be, okay, so we'll start with a, you know, I don't know any f equals 100 atoms either, but we'll start with a large F because I understand what's supposed to happen in large F. All right, my reference set of sites are these two, I, J. I'm looking at the correlator of those two with all other pairs. So for instance, the probability of having a singlet on this bond and this bond simultaneously is 0, right? That the whole rules are I can't have a bond in that thing, right? And then there's a 15% chance of having both a bond there, and so on. You may ask, why is this 25%? Well, that's because there's 4 symmetry-related ladder states, and we're in a quantum superposition of those 4, essentially. Okay, right? And so this is exactly what you would expect from a ladder. Okay, so now I'm going to show you the f equals 3, and depending on how you think about things, you either say, well, that looks like a ladder, or that certainly doesn't look like a ladder. So I would say with this size of system, we can't see if there is long range columnar order on this. We have a mean field theory, which I'll talk about in just a moment, which suggests there is a phase transition near f equals 2, which goes between, at small f, you actually get a Bose-Einstein condensate that's a polar state. And so certainly this may be indicative of either being near that phase transition or past it. There's also, we're kind of hopeful of trying to find some kind of spin liquid in this as well. And okay, so just to advertise the mean field theory, which is actually done by my collaborators a few years back. What it amounts to is writing exactly the Hamiltonian we have written down, and then do a mean field decoupling of it, and essentially do Begali-Abov and looks to where it can be self-consistent. Is what it is. And they did, in this paper here, they were looking at the case where they took the f equals 0 u to be different than all the other ones. And then this axis is looking at the ratio between those. 5 minutes? Great, perfect, that's just what I need. And so everything I've been talking about so far has just been where this ratio is really large, so it's over here. So as you see, that around f equals 2 or 3 were predicting this transition. I would not expect this to be a very reliable theory, but it gives you some indication. Okay, next we have the triangular lattice, which had this more interesting spin pattern. And so if I look at the large F case, the F equals 100, indeed I get a pattern which looks very much like this cartoon that's in the literature. So I wrote that there were two equivalent sets of these plaquettes that should be in the ground state. I only wrote one of them because with this as our reference bond, only one of them appear. We have only one overlap with one of them, and you definitely see that there are these visible plaquette regions. Again, when I go to F equals 3, things are a bit more ambiguous. Okay. All right, so why were we looking at that particular measure? And the answer is because that's exactly the measure you can get in the experiment. So you can imagine using our same trick of photo-association, but now going on to resonance. So this is very similar to some stuff that Randy's used to probe some spin correlations. And, so then, if you tune this onto resonance, you're going to get an atom loss term, which is dependent on nearest neighbors being in singlets. And so what you would do is you'd set up your state, flash this on for a short time, take a picture, look at where atoms are missing, and bin that. Then you start over, flash on your resonant photo-association, take a picture, bin that. And the histogram of where things are where pairs of atoms are missing is exactly the picture I was drawing on the last page. That's exactly what it gives. Okay. All right. So what are the problems with this? So Caden already asked about energy scales. You get pretty strong, pretty small gaps to excited states, and so there's really high sensitivity temperature, high sensitivity to magnetic field. I wanted this symmetry. It's easy to break this symmetry. Actually doing this photo-association is a non-trivial step. And then, typical atoms you can start thinking about. Maybe you'll get F equals 3. The patterns are a little bit ambiguous. The flip side of that is maybe these Fs are places where there's interesting things happening. Okay. Finally, I just want to point out there's been a couple other proposals and even some experiments looking at dimer models in cold atoms. The most famous, of course, is Marcus's experiments with the tilted lattices, which you can interpret as 1D dimer models, right? That the things can live on bonds. And Subir Sachdev talked both about these and about more generalizations in two-dimensional settings. The nice things about all of these ones is the energy scales are on the hopping level rather than on the super exchange level. So there's some fundamentally better aspects of this stuff, right, on those grounds. Peter Zoller also had some nice ideas about using Rydberg atoms, and you can sort of understand that the geometric constraints come about from Rydberg blockade. Okay, with that, I'm gonna conclude. If you have any questions, please ask.
Suppose someone in that class that you gave that problem to said, I'd like to work out this orthogonality for the entire many-body state. Then wouldn't they get a different answer?
So for the entire many-body states, actually, it's a nice exercise that if you take the overlap between any set of configuration like this,
why not take the overlap not between those configurations, but between like a 100 by 100 lattice configuration?
Yeah. So suppose I wrote a 100 by 100 lattice configuration. I put a set of bonds on one, and I put a set of bonds on the other. Right? it turns out there's a geometric way to answer that you get, is that you lay the two patterns on top of each other, right? And you can imagine that when you lay two sets of bond patterns on top of each other, you're going to get a bunch of loops. You can express the overlap, I think it's at 2f plus 1 to the number of atoms divided by the square root of 2f plus 1 to the number of loops. Something like that. You know, I'd have to write it down, but you can relate it to it's actually related to the number of loops in the system that when you do this overlap.
Kind of small, right, with those powers.
So if you have a lot of bonds being different, then indeed you get a very small overlap. Right.
So with this photo-association tuning, have you looked at what the off-resonant scattering rate is?
Yeah, I mean, so right. I mean, it's, you know, there's. Right, so essentially the question is how is omega related to your laser intensity, right? So what's the matrix element? And how big is your lifetime? Right? Those are the two questions, and then you need to right. So how far can you tune? That's a question of your intensity, right? So in principle, right? Based on gamma, you detune a certain distance, and then you ask, do I have enough laser intensity, right? And our estimates were these whatever, however many watts per centimeter squared, and you know the.
Well, I guess you probably detune so far before you run into another line as well. Have you looked at this for real atoms? I guess.
Yeah, so that's no. No, that's a mess, and there's so many lines, and this requirement that we're looking at in S equals 0, 1, yeah.
Yeah, so I had a question. You mentioned this Greenfield phase diagram.
Yeah.
So I didn't get it. Well, maybe you mentioned it. Are there any other calculations beyond Greenfield?
So there is this exact ionization calculation. There's the mean field calculation. If you look at just the Roxor-Kivelson model, there are a lot of calculations on that. You know, there's probably a dozen different approaches people use. A typical one is you map it onto a height model, and then there's a Monte Carlo algorithm that you can use on that. We've thought a little bit about some Monte Carlo algorithms that'll work on this model, but we haven't implemented any.
So how big is the exact ionization calculation?
So it was exactly the thing you were seeing. So it was 4 by 4.
That's a 4 by 4.
4 by 4. So you know, not state of the art, but it, you know, these things scale so badly, and really we want, because we're looking at ordered phases that have certain symmetries. You know, we want to keep to a square thing. And so 5 by 5, well, we have to go to 6 by 6 actually, right? And that's more work than it's worth, at least for us.
I was thinking, I mean, you were mentioning at the end Rydberg. Rydberg might be also a way actually to induce your interaction shift. Because there at least the lifetime is longer, and the induced flashback resonance there actually has been demonstrated by Harry Bosch and I think some losses are bad, but
yeah.
at least better than on the lower states.
Yeah, thank you.